All right, so in this lecture, we're going to see this generic reaction mechanism scheme that we're going to see over and over again for the rest of the chapter, because we're going to see that all aldehydes and ketones undergo the same type of reactions, which are nucleophilic addition reactions, okay? So what do these happen? So remember, when we are learning about resonance structures, we learned that if you have this asymmetric bond, by asymmetric, I mean in terms of electronegativity, it can rearrange itself like so. And this isn't a terribly favorable resonance contributor, but remember what we said about resonance contributors, even if they're not terribly stable, they do impact the behavior of the molecule. And you can see because of this resonance structure, something very key here, which is this positive charge on the carbon, right? So does that make it an electrophile or a nucleophile? Hopefully you said electrophile, and that is the basis of all of these ketone and aldehyde reactions, is that carbonyl carbon is electrophilic. You're going to hear me say electrophilic carbonyl carbon probably about 1 billion times, okay? And this can also just be illustrated just based on the electronegativity of the two atoms and the sort of partial positive charge you get from that polar bond, right? Both of these illustrating the same thing, which is that carbonyl carbon is electrophilic, relatively electron poor. Okay, so what we're going to see over and over again in these electrophilic reactions is you're going to start with your carbonyl carbon, right? And the thing to note about that is because it's sp2 hybridized, it's planar, meaning that carbonyl bond or that carbonyl group sort of lays flat with whatever it's bound to. And then you're going to have a nucleophile attack that electrophilic carbonyl carbon. And that's good. And then carbon can't have more than 4 bonds, right? So that's going to kick that pair of electrons up into this oxygen. Okay. Just note, because it is flat, you could have had the same thing coming from the other side. So these reactions are all going to be sort of not stereospecific. You can attack from either side. You're always going to get a racemic mixture. So good news, we don't have to worry about stereochemistry for this set of reactions. Okay, you may create a new chiral center, but you're always going to get equal amounts of both. All right, and then you'll go from your trigonal planar carbonyl group to some sort of a tetrahedral intermediate here. In this case, this oxygen now has a negative charge. It would have to accept a proton from a source of acid, water or something like that, and become an alcohol group. So these are nucleophilic additions. They're going to be the basis of what we see over and over again. Comparing aldehydes and ketones, aldehydes are more reactive than ketones for 2 big reasons. The first one, arguably maybe the more important one, aldehydes are less sterically hindered, right? Hydrogens are way smaller than methyl groups or ethyl groups or any sort of alkyl groups. So that hydrogens was just way more accessible. The other effect is that aldehydes have a larger positive partial charge on the carbonyl carbon because they don't have any electron donating alkyl groups, right? Alkyl groups tend to stabilize charge in a way that that you don't have with aldehydes. So that means, by sort of this logic, formaldehyde is the most reactive of all the ketones or aldehydes, because then you don't have any alkyl groups on there at all, super sterically accessible, and a lot of partial positive charge on that carbonyl carbon. One of the ones that we learned about, this was again back in chapter 12. We're going to go over it again in a few lectures, more specifically the carbon nucleophile lecture in particular. But just remember, these are Grignard reactions, and they have to take, one of the things we learned about Grignard reactions is that they have to take place under basic conditions, okay? Most strong nucleophiles only exist under basic conditions. Take, for example, the amide ion or the hydroxide ion, 2 great nucleophiles. Well, not those guys aren't going to survive under acidic conditions, right? If you tried to carry out a reaction with those under acidic conditions, you would just immediately protonate either one of them, Okay, so a lot of strong nucleophiles will react only under basic conditions. So the first thing we're going to learn is just this generic reaction mechanism scheme for basic conditions. Okay, again, we have this strong nucleophile that's going to attack that electrophilic carbonyl carbon. And then what's going to have to happen, this pair of electrons is going to have to bump up because carbon's not allowed to have more than 4 bonds. Okay, this gets us this. We go from our trigonal planar to our tetrahedral. This is another sort of sign of these reactions here. We have our tetrahedral intermediate. And then what often happens is that we're left over with a negative charge on that oxygen because that pair of electrons bumped up. That the second step is most often just some sort of proton transfer step. You cap off that negatively charged oxygen by having some sort of a proton donor, right? Water is a great one. Okay. Again, this is like this generic reaction mechanism scheme that we're going to see under basic conditions. So we're going to figure out insert nucleophile here kind of deal, and it's going to follow these same things. One thing to note about reactions that take place under basic conditions is that all of our intermediates are either neutral or negatively charged. There's no positive charges floating around. That's a hallmark of basic conditions. Is every step of the way you either have no charge at all, a neutral species, or a negatively charged species, but not any positively charged species. Okay. And now the same thing, but under acidic conditions. So a lot of weak nucleophiles will still react with aldehydes and ketones under acidic conditions. And the reason for that is that this first step is actually a proton transfer to that carbonyl oxygen, right? So you protonate the carbonyl oxygen. This creates this sort of thing right here, which we'll see in a second why, but it is a great electrophile. Right, so by having these ketones or aldehydes under acidic conditions, we can create these really banging electrophiles that will react with even weaker nucleophiles. And so this nucleophile will then attack this carbon here, bump that pair of electrons up, and now we have our alcohol group, our ketone or aldehyde has turned into an alcohol group, similar to before, right? So notice that the products are the same under acidic and basic conditions. The difference is the mechanism itself. Importantly to note that if you have a reaction mechanism under acidic conditions, you will always have either positively charged or neutral intermediates, okay? In fact, this right here is probably not the best nucleophile to have used because it has that negative charge. Most likely that's sort of signifies a good strong nucleophile, which would just react with our acidic conditions. So really what we probably should have had instead, if the book was being really good, is have this be hydrogen there and then have to do a step over here where we deprotonate that nucleophile. That's actually what we're going to see in our reaction mechanisms that take place under acidic conditions. Okay, that's positive. So this is kind of the rule of thumb. That the bottom line of these last two slides is to hammer something home. That is, basic conditions imply neutral or negatively charged intermediates. Acidic conditions imply neutral or positively charged intermediates. All right, and again, just to point out, right, I said that the first step under acidic conditions is actually the protonation of that carbonyl oxygen. And that creates this very powerful electrophile because, of course, this guy has this resonance structure available to him. That pair of electrons jumps up, and I'm left with what is the best carbon electrophile you can have, the carbocation. All right, so this is one that you're going to do in your discussions, is what takes place under acidic conditions between a halohydrin like hydrochloric acid, hydrobromic acid, and figure out the reaction mechanism to form this guy right here. Okay. I just want to say about these reactions that these aren't actually going to be like on our list of ketone and aldehyde reactions. because they strongly favor the reactants. So we can draw the reaction mechanism and stuff, but they're still going to strongly favor this reactant side. So it's not a really good way, you can't actually form this in any appreciable amount. Mainly because chlorine is just such a good leaving group that if you got to this point here, what's going to happen is this pair of electrons is going to come down and kick off that really good leaving group. Okay, but nonetheless, just to practice reaction mechanisms, this is what you'll do in your discussion, is under acidic conditions, the reaction between, I think, hydrobromic acid and a ketone. And it's going to follow very closely to this mechanism here. Okay,